All right, so let's graph this equation, clear out whatever else we had in here. And our first equation was, and you can use the fraction button in your graphing as well. So on the top of my fraction, I have x squared minus 1. And on the bottom of my fraction, I have x plus 1. And it's said to set up our window from negative 9.4 to 9.4 and negative 6.2 to 6.2. Now, depending on the version of the calculator, it may or may not do a good job of this. Oh. Is that what you got? Okay, does anybody have, so I have a newer version. In fact, I think the older versions might even be better than this. Does anybody have a graph that looks like this and there's an actual space missing? Okay, if the space is missing, that's even better. Okay, because what this is maybe your first ever graph that you've seen with a hole in it. It's got a hole in the graph. Okay? Sometimes with the newer calculators, they're fancier. They can plot more points, as it appears to have plotted on mine, that it gets so close that you can't even see that there's a hole in it. But this graph does have a hole in it. It has no vertical asymptotes, no horizontal asymptotes. So there's 4 more there. And I would like you to graph each of them and say which ones have asymptotes, what's the non-permissible value, and the non-permissible value, since x can't equal negative 1, we actually have a hole, and this hole, if we look at the graph and estimate it, you might estimate it to be at negative 1, negative 2. We're going to find out algebraically how that is later. Put arrowheads on the end of your graph and try the next ones. Let's see how you did on the next set of them. And for those of you that if the holes are not showing up on your graph, like there is a hole on this one right there, there is a hole on this one right there. With the newer calculator, we just figured out that if you set your window instead of from 9.4 to 9.4, apparently it has a higher resolution screen, so that means there's more pixels. You'll need to go from negative 13.2 to 13.2. And then your holes will show up. So, these are the graphs that we have for our next one. Notice that when you have a non-permissible value and there's no asymptote where that non-permissible value is, that's when you get a hole. And the coordinates of that hole will always have the x-coordinate, whatever your non-permissible value is. Now, if we try to estimate from this picture where that is, it looks like it's at negative 3. Again, I'm going to show you algebraically how you're going to be able to find that. Because if it's not a nice number, you're not going to want to estimate by just looking at a graph. But this one too, it has no asymptotes, but it has a non-permissible value at 2. That means if we're going to label our hole, it's going to be at 2, and if we would estimate where that is, 1, 2, 3, 4, it looks like it's at 2, 4. Again, we should have arrowheads on the ends of all of our graphs. And since these are just screenshots of our calculator, I need to take out my red pen and add my asymptotes in there. With your asymptotes, you're going to also want to label them. This one's at x equals 1. This one's at x equals negative 2. And again, we notice that when there is an asymptote, that asymptote always is connected to your non-permissible value. So non-permissible values either result in holes or they result in asymptotes. Now, graphs 2 and 3 here have something strange happen in that we also have diagonal asymptotes, which we'll call oblique asymptotes. So this was group 1. If we look at all of the equations of group 1, how would we categorize them? How would we notice what kind of pattern do all of the equations have in common? So right at the top of group 1, you've got a little bit of space right beside group 1. We're going to characterize some of the things that we noticed. First of all, the form of all 5 of these. Can you see that all 5 of them had an x squared on the top with something and an x on the bottom? In other words, we had a quadratic equation which has a degree of 2 over a linear equation which has a degree of 1. The degree of a polynomial is its highest exponent in the biggest power. So since the highest exponent is a 2 on the top, it's a quadratic or a parabola divided by a line. Okay? And the characteristics that we noticed, there's 2 of them. You either have holes or vertical asymptotes with oblique asymptotes. And that oblique word means diagonal. Why don't they just use diagonal?
Sounds cooler.
Because, yeah, it sounds cooler. Right? I can say during math class I was working on my obliques today. So now the question is, how do we decide if something has a hole? How do I know from the equation that this first one had a hole and not an asymptote? Okay, what could I do with this equation? I could factor the top. And if I factor the top, I would get bracket, 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 bracket. It's a difference of squares. X plus 1, x minus 1, divided by x plus 1. What could you do with that? You could cancel. And when you can cancel out your non-permissible value, it doesn't make it permissible. You still can't plug in -1 into this equation, even though, what does this simplify to? It simplifies to y equals x minus 1. What kind of graph is that? Linear graph, a straight line. Did we come up with a straight line? Yes. Does that straight line look like y equals x minus 1? Does it look like it has a slope of 1? Does it look like the y-intercept is -1? Yes. What's the difference between it and a regular line? It has a hole in it. It has a hole at -1, -2. How do I find the coordinates of that algebraically? Well, after you simplify, what happens now if you plug in your non-permissible value? -1 minus 1 would be -2. So on the line, you would have the point -1, -2. But since that value is non-permissible, that is the coordinates of your hole. So let's look at the other ones that had holes. Can you factor this one? X and x, plus 2 and minus 1, sure enough, our non-permissible value got canceled out. Does that look like the equation of x minus 1 again? Yes. Our non-permissible value happens when x is -2. What would happen if you plugged in -2 into y equals x minus 1? You would get -2, -3. And so that's the coordinates of your hole. The second one here, the x squared over x minus 1. Can you see that you can't factor the top? Okay. The third one, x squared plus 2x plus 1, you can factor the top. The top factors to x plus 1, x plus 1, all over x plus 2. But after you factor the top, it doesn't cancel out. So when your non-permissible value doesn't cancel out, you get vertical asymptotes. When your non-permissible value cancels out, you're going to get a hole. And so can you see in the last one I have a common factor I can factor out of the top. There's a 2x in common, leaving me with x minus 2 over x minus 2. Those simplify. And so this equation just becomes y equals 2x, which is a straight line with a y-intercept of 0 and a slope of 2. If I want to figure out where the hole is, my non-permissible value is 2. If I plug in 2 for x, I would get the point 2, 4. And so that's the coordinate of my hole. This is pattern number 1. These are the things that happen when you have a parabola divided by a line. Group number 2. Try each of these, draw the sketch of the graph, and then we'll characterize them. All right, let's see how you did. Did you come up with these graphs? And drawing in the asymptotes on each of them. Now, each of these graphs still have non-permissible values, and if you look at all of the equations, you can factor them to see if things cancel out. None of these have holes. So one thing that we're going to find with all of our equations is that things are going to be easier if you can factor things completely, because that is going to be the main thing you're going to use to find out if your graph has any holes. On this one here, you can factor out a -2 out of the top. So a couple of things that show up in these graphs and a couple of patterns that we can see. First of all, whatever our non-permissible values are in this case, they always become vertical asymptotes because they didn't cancel out. So your non-permissible values will always be either vertical asymptotes or holes. If a non-permissible value cancels out, it becomes a hole. If it doesn't cancel out like it didn't in any of these, it stays, they will always become vertical asymptotes. And so that's why we have a vertical asymptote here at x equals 1, here at x equals -2 and x equals 2, and here at x equals 1. Now these ones all ended up with a horizontal asymptote. There's one at y equals 3, one at y equals 1, one at y equals -2. So we could kind of estimate that from the graph, just looking at it, but how can we tell from the equation? Okay? So let's start talking about group 2. In group 2, the degree on the top and the degree on the bottom is the same. So function number 1, it was a line divided by a line. Function number 2, a parabola divided by a parabola. Function number 3, a line divided by a line. So if your highest degree is the same in both of them, then you're going to have a horizontal asymptote. So our characteristic, if we're going to just write down what the main characteristic of all of these ones are, is that we have both horizontal and vertical asymptotes. So how do we find out where those horizontal asymptotes are? Well, what I'm going to do, I'm going to take out my highlighter, and since the degrees are the same, again, horizontal asymptotes tell you what happens when x gets really big, either huge positive numbers or a really big negative number. Okay? And so in this question, I have x minus 1 on the bottom. And if we think about this as money, right? And we say 1 is $1 and x is how much money you have. Okay? If you're really little, right? And your parents give you $1.25 to go to the Coke machine to get a treat. Now it would be like probably $2.75, right? If you want to get a drink from a Coke machine, it's probably $2.75. If on the way to the Coke machine you lose $1, is that significant? Yes, it makes a big difference. Okay? But now you imagine you are one of the richest people in the world. Who are the richest people in the world? Who's the guy that owns Amazon? I think he's the richest now. I don't even know his name. I haven't invited him over for supper for a couple days. Anyways, well, it used to be like Bill Gates, richest man, right? Bill Gates is walking down the street, he loses $1. How is that going to affect him? Nothing, right? It's not going to have any effect on him whatsoever. And so when x gets really, really big, that losing $1 doesn't make a difference. So when x gets really, really big, what we can sort of do is just say, well, 3x is important and x is important, but the other things don't really make a difference anymore. And if I just look at 3x over x, what is 3x divided by x? If you simplify 3x over x, you just get 3. And that will always be your vertical asymptote. Because if x was really, really big, like 1 billion, can you see that you would have 3 billion divided by 1 billion minus 1, which is really, 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 really close to 3. So when x gets really big, if we ignore all the things that are small, we can find out what the asymptote is. And the way that we do that is we look for that highest degree. In the second one, highest degree on the top is an x squared. Highest degree on the bottom is the x squared. You can really forget about the minus 1 and the minus 4. What does x squared over x squared simplify to? 1. And that's your horizontal asymptote. And the last one, the highest degree on the top is an x. You've got a minus 2x on the top and an x on the bottom. If you ignored everything else, what would minus 2x over x simplify to? Minus 2. Group 3. So here are the first 3. And if we add in our asymptotes, this one has an asymptote there. And if we look at all of these to see whether or not they can be factored or not, the first one cannot be factored. The second one negative x and x make an x squared. 3 and 1 plus plus. So 3 and negative 1 are non-permissible values. And the third one cannot be factored either. When we look at the next two, drawing our asymptotes, neither of them can be factored. And what happens that's weird in the last graph is that there is an asymptote even though our graph goes through it. So if we would label our asymptotes, we have y equals 0, y equals 0, x equals 0. Go back a page and do the other ones. Y equals 0, y equals 0, y equals 0, x equals -1, and x equals 3, and x equals 0. So how would we characterize group 3? Group 3 is when you have a function divided by a function, but on the bottom, the degree is larger. So the first three have a constant divided by a parabola, something over x squared. So the degree on the top is 0. The degree on the bottom is 2. In the next two, you have a line divided by a parabola, so the degree on the bottom is 2 and the degree on the top is 1. So in all of these, the degree is larger on the bottom. And you can use the same strategy, but you have to be a little bit creative for finding out your horizontal asymptote that we did the last time. Or you can remember that if the degree is bigger on the bottom than the top, you will always have, as far as its characteristics goes, you will always have a horizontal asymptote at y equals 0. Always have a horizontal asymptote at y equals 0. And the way that you can figure that out is if you look at this first equation, what's the highest degree in the whole thing? Is a degree of 2. So if I have a degree of 2 on the bottom, how many x squareds do I have on the top? I don't have any. Would you agree that I could rewrite the top as 0x squared plus 6? I mean, it's still 0, but you'd say, well, why would you want to do that? Well, if I then highlight my highest degree, which is my x squared, I have 1x squared on the bottom, 0x squareds on the top. What is 0 divided by 1? 0. So I could do that for each of these. I have a -1x squared on the bottom of the second one, 0x squareds on the top. What's 0 divided by -1? 0. The next one. I have 1x squared on the bottom. I have no x squareds on the top. 0. Careful here, the biggest degree is 2. I have 1x squared on the bottom, but I have no x squareds on the top. 0. So whenever the degree is larger on the bottom, it's going to mean that you're going to have an asymptote at 0. Why does that happen? Let's look at 4x and x squared. And let's think about when x gets big. Right? If you had $100 and someone says, I'll multiply that by 4, I'll give you 400, you'd be like, yes, that's bigger. That makes me happy. But if someone said, or you could take your $100 and square it. Well, 100 squared is 10,000. You're like, well, 10,000 or 400. So you're like, man, I wish I would have paid attention grade 6. Which one's bigger? Okay, I'll go with the 10,000. And what happens if it's even bigger? Like if it was $1 million, 4 times a million, well, that'd be pretty awesome, 4 million. But 1 million squared is much more powerful and gets bigger way faster. So when x gets really, really big, 4x is big, but x squared is bigger. And if you have a big number divided by a big, 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 big number, it's going to get close to 0. So how come it crosses the asymptote in the middle? Again, horizontal asymptotes tell you what's going to happen to the function when x gets really big with positive numbers or really big with negative numbers. It doesn't necessarily tell you anything in the middle. And so if we look in the middle here, what happens when x is 0? You'd have 0 over 1. And that would be that point at 0, 0. And so it actually goes through our asymptote. And so sometimes it does happen that a graph can go through a horizontal asymptote in the middle.
But never through a horizontal, never through a vertical.
Never through a vertical, because a vertical asymptote represents a non-permissible value, whereas a horizontal asymptote represents the end behavior of a graph, what happens when the x values get big. And so this is group 3.